Welcome once again to a tutorial on the 8085 interrupts. Okay, and here I'm gonna show how to write a program on the based on interrupting the 8085. Okay, so we're gonna bring a problem statement. Okay, here we are with our problem statement. So it says that we need to write a program to display an 8-bit data of 00H continuously. Okay, and also make a provision for any interrupt received during this time at 0018H. Now this address, that 0018H, it seems familiar, like we've seen it somewhere. Okay, no problem. I'll bring the table that we had seen in the previous tutorial for all the RST interrupts. Okay, so here's our table, and now if we just check the call locations, okay, so we can see the 0018H memory address corresponds to, the interrupt request of RST3. So this is the interrupt instruction, that's RST3, for which we would have to design or write our program. So let's read the rest. And now it says, well, flash the 8-bit data of FFH once at port 1. Okay, for 1 second if interrupt is received. Alright, so here port 1 would refer to any output port of the 8255A chip. So if y'all are thinking of incorporating the 8255A chip hardware within this particular program also, then kindly check out our tutorial on the 8255A chip and how to get its address, output port address and all, so that way you can just use it. Okay, so now let's just get on with our program, but before we do that, we need to take a look at what sort of hardware we would use to receive this kind of an interrupt signal. And here is our hardware for the corresponding interrupt based program which we're gonna write. Okay, and we're gonna send the interrupt request signal at the INTR pin of the 8085 using this switch S1, which is currently in the open state. Okay, so meaning there is a logic 0 voltage level falling on the INTR pin of 8051, meaning 8085, sorry, meaning that no interrupt request is available currently. Okay, so now it says that we are supposed to output our the code of FFH at port 1. Okay, and we're also supposed to display the 8-bit data of 00H, and this also we will basically, well, there is no particular mention of any kind of port, so we are gonna assume that we are supposed to display the 00H data at port 1. Okay, so we just take it by default. Okay, so we can just display it at port 1 on any other kind of port as we might desire. So not a problem. So we can just go with this assumption over here. And now talking about port 1, as I said, you can just take this port 1 or you can just assume it to be any port. Okay, this could be basically, well, any output port of the 8255A chip. Okay, so for any further reference, just kindly check out our tutorial on the 8255A chip. And well, so let's just get on with our program. Okay, now before beginning our program, we assume that the available memory address range, okay, the available memory address range is, well, it's basically within the limits of, well, 0000H to that of, well, 3FFH. So this is going to be our available memory address range. Okay, so we just will assume 1 and think that our system basically has this sort of a usable memory address range. Okay, so now when we are going to write our program, we need to keep in mind that the program would consist of, well, 3 parts. Okay, one is a main program or a main program body from which we're going to call the interrupt. Okay, next is the interrupt service routine. Okay, so this is going to be the interrupt service routine. That's the subroutine for doing the necessary things as instructed in the program whenever the 8085 is interrupted. And finally, since we have to display the code FFH for about 1 second approximately, so we also need to have a delay subroutine. Okay, so we need to have a delay subroutine that just supplies or creates a delay of approximately 1 second. Okay, so these are the three basic parts that our program would basically have. Okay, now we can start writing our program from 0000H onwards, but we won't do that. Why? It's because if you take a look at this table, then you'll see that, well, lots of call locations depending upon all the RST instructions that are, I mean the RST interrupts that are just present over here. Lots of their call location are placed where the first 2 higher bytes of memory address is 00. Okay, so they are just starting from the memory address 0000H, and many of them are present. Okay, so there are 8 different call locations already reserved for these RST instructions, which we have configured using an external hardware, as this picture shows you. So we are not going to utilize the memory location of 0000H for writing our program, because otherwise it will just, well, the program codes will just interfere with these call locations, and that would create a malfunction. Okay, so instead what we'll do is that we'll start writing our program from the location 1000H onwards, so that way things would just be secure enough. Okay, so let's get on with our program finally. So our program begins at the memory address of 1000H. Okay, like the one we've just assumed over here. So the very first thing that we need to do while writing the program is that, since we're working with interrupts, and these interrupts are basically a form of call instruction, and they're just going to transfer the current status of the main program, okay, that the 8085 is going to execute into the stack memory. Okay, so we need to declare a stack memory area first. Okay, so this is very, very important. If you forget to do that, then your program contents might not be saved. Okay, so we have to declare the stack memory location first. So we would assume in this case highest location of, let's say, the ending of the memory location, that is, as you can see over here, as we had just assumed, that's 3FFH. We can just declare our stack right over here. So we're going to declare stack memory at 3FFH. So that's the very first thing we're going to do. So the very first line of our program is going to start with declaring the stack memory. So we're going to write LXI SP, that's the stack pointer, okay, 3FFH. So our stack is specified at 3FFH, so that's the beginning address or memory address of our stack. And then what we're going to do is that we're just going to enable the interrupt. Since our program needs to accept interrupts, we're just going to enable it. So we're going to write here EI, meaning enable interrupt. Okay, and after the LXI command is given, we can just see that it's basically a 3-byte instruction. So the next memory location where EI would just be placed would be 1003. So 1002. That's better. Okay, so we have EI over here. Okay, next, now that we have enabled the interrupt, we are gonna load a data byte of 008. Now, since the program says we are supposed to display the output code, I mean an 8-bit data of 00H at port 1, okay, so we are gonna load the accumulator for doing the same. So we're gonna write here MVI A, 00H. Okay, so we have just loaded the accumulator with it, and then we're just going to send it to the output port. So we're going to write here out, okay, and we're just sending it to port 1, so out port 1. Okay, so MVI is going to be placed at 1003. So there you go. And now, since this is a 2-byte instruction, MVI A00H, so after that we're going to have the out instruction placed at 1005H. Okay, and then after we have just written this, we're just gonna declare a loop over here, since we need to display the 00H content continuously. So we're gonna give a jump statement. So we're gonna give an unconditional jump statement. So that is JMP, which is an unconditional jump statement, and we're just jumping onto the level J1. Okay, we're jumping to the level J1, where J1 actually corresponds to this part over here. Okay, it just goes on to this part, that is MVI A00H. Okay, so in that case, its corresponding memory location is actually 1003H. So J1 actually corresponds to the memory location 1003H. So you're gonna send, or you're gonna input this 1003 memory address while you're just sending or loading this particular program on your 8085 microprocessor trainer kit. Okay, so, and the JMP instruction is going to be placed at the memory location of 1007H. Okay, now since the out port one is basically a 2-byte instruction. Okay, now what we see here is the main program body. Okay, so this is basically our main program body. So this is our main body. Okay, and now whenever there will be any kind of interrupt, okay, this main program would direct the program control to the specific memory call location, depending upon which sort of interrupt request it receives. Now our problem statement tells us that we are supposed to write the interrupt service routine at 0018H, meaning that we can basically assume that we are gonna get an RST interrupt request of RST3. Okay, so that's why we need to write the service routine at the 0018 memory location. Okay, so in that case, what we would do is that we can just take the help of this hardware. So we can just see how this hardware has been configured, and whenever the interrupt is falling, okay, we can just assume that the switch S1 is being closed at this particular moment. So as you can see over here, okay, so whenever this happens, so even if you just close the switch S1 momentarily and then open it, then although there is no longer logic 1 signal falling on the INTR pin of the 8085, but still there is a flip-flop present at the INTR pin inside the 8085 chip. Okay, now that flip-flop gets set to logic 1 level, and this just helps to trigger an output of logic 0 from the INTA bar, that's the interrupt acknowledge pin, and this logic 0 signal in turn enables the tri-state buffer chip. Okay, and due to enabling the tri-state buffer chip, it would just send the corresponding binary code corresponding to the RST3 request. Okay, that is whose hex code is equivalent hex code is DFH into the 8085 through its lower order address data bus. Okay, so this is exactly what's going to happen over here, and for our program part, we need to write a suitable service routine in order to handle all that. So what we are supposed to do is that whenever we need to write the service routine, we need to keep one thing in mind, that we need to save the contents of the accumulator and the PSW, that's the program status word, that's the flag register. So we are gonna actually save, okay, we're gonna save contents of the register A, that's the accumulator, and the flag, okay, on the stack memory. Okay, so we're gonna save it on the stack memory, so that whenever the program control just returns to the main body, okay, then the normal operations can just be resumed once again. So we start writing our service routine from the location 0018. Okay, so let's just go back over here. So we're writing, so this is going to be our service routine, so I'm just going to specify it over here. So this is our interrupt service routine, so better it is I just write it that way. So this is our interrupt service routine. Okay, so there you go. Now in this interrupt service routine, the location begins from 0018H. Okay, so that's where our first line of the interrupt service routine is gonna be placed. So first of all, we need, as I said, we need to save the contents of the register A and the flags on the stack memory area. Okay, so now we have already declared the stack, so we're gonna save it over here. So we're gonna write here push. So we're gonna use the push statement to just save the data of the accumulator and the flag register on the stack. So push PSW, where actually the accumulator and the flag registers are together. Okay, accumulator plus flag are well together referred to as the PSW. Okay, and PSW actually stands for program status word. Okay, so it actually stands for program status word. So this is what actually this PSW abbreviation stands for. Okay, so we're gonna write here push PSW, that's all. And then after that we're gonna load the accumulator. Now that the accumulator contents are already saved on the stack, so there's no problem in using it. So we are gonna load a data. Okay, we're gonna load into the accumulator an 8-bit data of FFH, since we're supposed to display it for 1 second, okay, at port 1. So, and after we do that, we are gonna send it to the port 1. So out port 1. Okay, there you go. And now we need to display this code or this 8-bit data for at least 1 second. So we need to call a delay subroutine. So we're gonna call a subroutine named delay. Okay, so this is delay is just the name of a level where the which actually corresponds to a memory location where the delay subroutine is placed. So let's just write this down and then we can go to the delay subroutine. Okay, so now we can just see that whenever the program control again returns to the main body, then we also need to ensure in the service routine that the contents of the accumulator and the flag registers that we had just saved on the stack, okay, that we just saved on the stack memory area, okay, they can just be sent back to the accumulator and the flag register once again. Okay, and that provision we need to provide right over here. So we are gonna write here a statement that is pop PSW. So now that we have just displayed the FFH at port 1, okay, and we have just called the delay of delay subroutine that we just supply or display this 8-bit data of FFH for 1 second. Now that all the tasks are done, we are supposed to return to the main program. Okay, but before we do so, we need to ensure that the operation assumes normal. That was just prior to the interrupt request. So we need to just send the entire contents of the accumulator and the flag registers right where they previously belonged. Okay, so that's why we need to we need to just execute this thing, that pop PSW once again. So this just ensures this area of actually restoring the contents of accumulator and the flag registers. And after we have just popped out the data, we need to ensure that the interrupt requests are enabled once again. So we are just going to enable the interrupt process once again, so that after the program returns to the main body, then again we can just receive, the program can basically receive any other interrupts. Okay, so now that we have just done so, we are just going to return. So we're going to use the return statement over here, and that's the end of the interrupt service routine. And here we have their corresponding memory locations also. There you go. Okay, now you might be there could be a question popping up in your mind that, well, we are actually using up all the space of the call locations. Okay, now as this table illustrates that, well, 0020 and all, this is also a call location, that's 0020, which is just being used in writing the interrupt service routine right over here, and so is 0028H, which just corresponds to another such call location. I'll tell you why we can do that, because here we are just designing the program for the RST3 interrupt request, and once you've just constructed your required hardware for a particular interrupt request, I mean a particular RST interrupt, okay, then you don't need to or you can, I mean, this hardware is just, you know, basically hardwired. You cannot make any sort of changes over here, okay, until and unless you just change the hardwired connections. Okay, so actually we're having not all 8 of these RST instructions simultaneously, but we're actually having only one RST instruction interrupt, okay, at a particular time. So due to that, we don't need to worry about the rest of the call locations, because we have already obtained one, that is for RST3. Okay, so I guess that should, you know, satisfy your doubt. Okay, now that we have just completed the interrupt service routine, we are gonna go to writing our delay subroutine right over here. So this is gonna be the delay subroutine. Now we are gonna start writing our delay subroutine from the memory location 1100H. Okay, now you can see that the main program body, well, that doesn't extend beyond 1007H. So if we just place our delay subroutine at 1100H, then there's no risk of having both the codes just overlapped. Okay, so in this case we're just gonna write the delay over here. So we're gonna begin by loading the register C. Okay, we're gonna just start loading the register C with 03H, that's an 8-bit data, and then we're gonna write here, we're gonna load the HL register pairs, okay, with a 16-bit data of FFFFH. All right, and then we're gonna decrement it. So we're gonna write here DCXH, okay, and then J and Z. So jump on no 0 to the level J1, where J1 corresponds to DCXH. I'm gonna give you the memory location later. Okay, and then again, after this is over, we also need to decrement the content of the register C, so DCRC. Okay, and also another jump on no 0 conditional jump statement, and this just transferred the control to J2, where J2 is actually the level where we have the statement LXI H FFFFH. Okay, and after all this just happens, we are just going to put a return command. So that just completes the code required for our delay subroutine. And for the memory locations, well, there you go. So as we have seen that our delay subroutine starts from 1100H, so this means that wherever we're writing call delay in the interrupt service routine, this delay level, well, actually should correspond to the memory location 1100H. So you're gonna input this 1100H memory location while you're just entering this program into your trainer kit. Okay, so that's done, and also we can see over here that J1 would correspond to the memory location 1105H, and also J2 would correspond to the memory location 1102H. There you go. So that just completes our entire program, where we have successfully sensed an interrupt, okay, and written a corresponding service routine to output FFH at port 1 for 1 second. Okay, and this delay subroutine, if you just will calculate in the way that I just showed in the previous tutorial, you'll find that there is a time delay. Okay, the time delay that is generated by this delay subroutine is approximately equal to 1 second, or more precisely, so this is just a prox calculation, and more precisely it is actually somewhat around 1.05 seconds. That's the exact delay that you'll be getting from this delay subroutine. Okay, so that just brings us to the end of this tutorial, and we're gonna see you next in the forthcoming ones. Okay, so till then, it's just gonna be a short goodbye, and thanks for watching.